can't draw curved three-dimensional universes. Can't do it. But I can draw curved two-dimensional universes, so these are analogies. And our universe, if we're a closed universe, you can understand physically what a closed universe would be like. Space would close in on itself. So if you look far enough in that direction, you'd see the back of your head. If the universe is closed, okay? And if it's open, you wouldn't. It would be infinite. And all that sounds nice, but operationally what's really important is, in a closed universe full of matter, it will expand but eventually stop and recollapse. An open universe will expand forever without stopping, and the boundary between the two is something called a flat universe. And in a flat universe, the universe will expand forever and slow down and never quite stop. And as you add mass, you go from an open universe to a flat universe to a closed universe. So we really wanted to know how much mass there was, not just to know what the energy of empty space was, which we knew was zero, but to literally know the future. And that, again, that is really why I got into physics, into cosmology, because it turns out the dominant mass in the universe is something we can't see that I thought I could have something to say about. And I wanted to know if there was enough mass to take us from an open to a flat or a closed universe. So we're weighing the universe, and as I say, in our solar system, we have weighed it. We have weighed it, and we can use that, in fact, to measure. We can use gravity to weigh the solar system, because Kepler discovered the planets moved around the sun in a certain simple way, and it turned out we could use that to weigh the mass of the sun. Using the speed of those planets around the sun, we could use it to measure the mass of the sun. We can use it to measure the mass of the galaxies. But if you want to measure the mass of the universe on larger scales, you have to be trickier. You can't use Newton's laws. But we can use general relativity to measure the mass of the universe. And now we're almost at the present, because these pictures are about 10 to 15 years old. This one in particular. We can use a picture like this to measure the mass of the universe and determine how much stuff there is. This is a cluster of galaxies. The biggest bound objects in the universe are clusters of galaxies. Galaxies like to hang around in clusters. Our galaxy is in a cluster called the Virgo cluster. And the point is that since clusters are the biggest bound objects in the universe, anything that can fall into anything will fall into a cluster of galaxies. So if we can weigh the mass of a cluster of galaxies, we weigh everything. Okay? And here's how we weigh it. This picture is literally worth more than 1,000 words. It's another Hubble Space Telescope picture. And it demonstrates a phenomenon that Einstein first proposed in 1937, I think. He said it would never be observable, however, because he underestimated observers, which is easy to do if you met any. What you notice here in this cluster of galaxies is that these weird blue things. You see those weird blue things? Well, those are not many different galaxies, but different images of a single galaxy. Because Einstein realized in 1937, if mass curves space, then if you have a big distribution of mass, and if you have a bright object behind that distribution, the light will go around, be bent, and come back. And you can see multiple images of a single object. This is what we call gravitational lensing. And the mass distribution is very irregular, we produce lots of images. If you take a cut glass goblet and look through it, sometimes you're going to see many different images of the room, because the light gets bent in a lot of different ways. With a mass distribution, the same thing can happen. And this is that phenomenon that he first predicted. And in fact, we now see all of these blue things are different images of the same galaxy located 2 billion light years behind this cluster, which is about 3 billion light years away. And the mass in this distribution has sometimes magnified the image, distorted it, bent it. But the great thing is, because we understand general relativity, we can work backwards and say how much mass is in this system and how is it distributed to produce that image. And we can invert the image, and this is an inversion of that image, and this is where the mass is in that cluster. In order to produce the image you saw, you need the mass to be here, and all these spikes, by the way, are where the galaxies are. But the first thing you should notice is that most of the mass in that system is between the galaxies. It's where the galaxies aren't. All throughout here. 90% or more of the mass of this cluster is made of stuff that doesn't shine. This stuff, physicists with their incredible linguistic perspicacity, has called dark matter. Okay? And what we've discovered is that it's not just true for this cluster, it's true for every cluster, it's true for every galaxy. Over 90% of the mass of stuff in the universe doesn't shine. And there's enough of it that we now are almost certain, and what makes it exciting is we're almost certain that it's not made of the same stuff as you and I are. It's not made of protons or neutrons or quarks or any of the common stuff that makes everything in this room. It's a new type of elementary particle, we think, and that makes it exciting because that means it's not just out in the cosmos, it's in this room. It's going right through your bodies and mine as we fall asleep during this lecture. Okay? And that means we can do experiments here on Earth to look for it. And we're building detectors here on Earth underground to look for this stuff. And if we discover it, we'll really discover the composition of most of the mass of the universe. And in fact, the other thing that makes it extremely exciting is we may not have to wait to detect it from these detectors. Right now, we built a big collider in Geneva, Switzerland, the Large Hadron Collider, which, as you know, is going to turn on and produce a black hole that's going to destroy all of us. It didn't. But it may actually produce these particles that were last produced at the earliest moments of the Big Bang. So it's a race right now to see whether we can detect this dark matter underground in laboratories or whether we can create it in accelerators here on Earth. Either way, when we do one or the other, we'll discover the composition of most of the mass of the universe. Now, having done this, I told you you could measure the mass of the clusters. I didn't give you the answer. Here's the answer. I can hear all of you take a deep breath. Okay? Well, in physics, whenever we have a really important number, we give it a Greek letter called omega. And omega makes it sound scholarly. Omega is the ratio of the total amount of matter that actually exists in the universe compared to the total amount of matter you need to make an exactly flat universe. So if omega is 1, the universe is flat. If omega is less than 1, the universe is open. If omega is greater than 1, the universe is closed. So this was the holy grail of physics for the 20th century, to measure omega, to find out what the future of the universe would be. And we measure it, we find out omega is 0.3. It's less than 1. The universe is open. That is an amazing result. The problem is, we theoretical physicists knew the answer. We knew omega had to be 1. Why did omega have to be 1? Because a flat universe is the only beautiful universe. And the damn observers were getting it wrong, as they tend to do. And it was a really big problem. And now, in the context of this lecture, I can explain, as I might not in other audiences, why a flat universe is the only beautiful universe. It comes back to the title that was given at the beginning. What makes a flat universe beautiful is in a flat universe, the total energy of the universe is 0. Precisely 0. Now, how can the energy of the universe be 0 with all sorts of stuff in the universe? Well, gravity is wonderful because it not only has positive energy, it has negative energy due to the gravitational attraction stuff. We call negative potential energy. And in a flat universe, everything adds up. So the positive energy of mass, of particles, is cancelled exactly by the gravitational potential energy of attraction of all those particles, and the energy of the universe is precisely 0. That is why a flat universe is the only beautiful universe. Why? Because if the universe started from nothing, what do you think its total energy would be? 0. Now, this is a real problem. This is the kind of problem that, in fact, is unique to science. Because although we knew the answer, unlike religion, if this was the real answer, we'd have to change our minds. Okay? And the point is, it's a profoundly important result. But we have to be, when you're measuring the universe and you're beginning to learn about the universe, you have to decide, you have to do more than one measurement to see if you're right. Okay? And, well, by the way, I should say, here are experiments that we actually an example of an experiment to detect dark matter underground. It's really simple. You can do this at home. Take germanium, take the germanium chip out of your computer and cool it to 1/1000th of a degree above absolute 0. Or go up to Edmonton or something, I don't know. And then put it deep underground, and then just wait. And we can calculate the billions and billions of dark matter particles that are going through that chip of germanium. About once each year, one of them will scatter off that pool of germanium, depositing enough energy So these detectors are being built. Actually, I proposed them about 25 years ago. It's taken a while for them to build them. And they're around the world, and maybe these will detect dark matter. But the important thing is, I told you we measure omega, and omega tells you the ratio of the real total energy of the universe over the energy of a flat universe, and that's how we try to determine the geometry of the universe. But wouldn't it be better if we could just measure the geometry of the universe directly, and then see if the universe is flat or not? See if it's open? That would be a much more direct way of determining the answer to the question that really interests us. And again, when I was a student, I would have never believed it was possible. In fact, 20 years ago, I wrote a proposal I'd forgotten on how to measure it, but I still wouldn't believe it was possible, but now they've been able to do it. And I want to show you. It's one of the most remarkable measurements in cosmology. Well, it's changed everything. Now, to figure out how to do this, you've got to ask yourself the question, how would you measure the curvature of the Earth if you couldn't go around it and you couldn't go into space to see if it was a sphere? Okay. Well, very simple. You take a triangle, and then you'd ask a European high school student, maybe a Canadian high school student, what's the sum of the angles in the triangle? You certainly wouldn't ask an American high school student that question. And when you did, they tell you, oh, the sum's 180 degrees. Okay? But that's because they learned the geometry from Euclid. On a sphere, it can be quite different, for example. On a sphere, I can draw a triangle like this. I can go along the equator, I can make a right angle, go up to the North Pole, make another right angle, and come back down to the equator, and I have a triangle now with 3 right angles. 3 times 90 is 270. So if I wanted to know that the Earth was curved, I would just have to draw a big enough triangle and see that some of the angles was not 180 degrees. It turns out that for different reasons, this is precisely true for a curved 3-dimensional universe too. All we have to do is measure a big enough triangle, measure the angles, and see if they add up to 180 degrees. And that's been possible in the last decade because of one of the most important observations in cosmology, the cosmic microwave background radiation, the afterglow of the Big Bang. Radiation that's been coming at us from the beginning of time. And let me just describe to you where that radiation comes from. It was discovered, by the way, by accident in New Jersey, of all places, in 1965 by 2 people who did not know what the hell they were doing. But they won the Nobel Prize anyway, which point says something. Because it doesn't matter if you know what you're doing, it was an important discovery. And what we do now when we try to measure is we have a microwave antenna here on Earth. We look out and we see galaxies that are maybe 1 billion light years away. When, if the universe is expanding, it was once smaller. And if it was once smaller, it was hotter. And if you go back to a time when the universe was about 100,000 years old, almost 14 billion years ago, it was 100,000 years old, the temperature of the universe was 3,000 degrees above absolute zero. At that temperature, the energy of the radiation is so hot that it breaks apart matter. All matter, the dominant matter in the universe is hydrogen. It breaks it apart into protons and electrons. So instead of having neutral matter, you've got charged matter. We call that charged matter a plasma. Plasma is opaque to radiation. You can't look through a plasma. So if we try and look, I mean, after all, the universe is 14 billion years old. You might think if you looked far enough away, you'd see the Big Bang. And literally, you could see the Big Bang if it weren't for the fact the universe got opaque. If you go back in time when it was 100,000 years old, you can't see before that, because the radiation can't make it to us, because the universe is a plasma. That's fine, but if we move the film forward, when the universe was 100,000 years old, at that point, the universe cooled down to where protons could capture electrons, matter could become neutral. Neutral matter is transparent to radiation. And I can see all the way back there. It's like this wall. I can't see past the wall because it's opaque. But I can see the wall, well, because the wall absorbs radiation from those lights and then re-emits it at its surface, and the air is transparent, so I can see all the way back to the wall. So when I look out at the universe, if there was a Big Bang, I should expect to see radiation coming at me from all directions from that wall. That metaphorical wall, if you want. And that radiation, which was 3,000 degrees, has cooled as the universe has expanded by a factor of 1,000. And now it's about 3 degrees above absolute zero. And in fact, it was recently measured to 5 significant places by some other people who won the Nobel Prize. And the reason they won the Nobel